Mathematics, how much gold can you hold in an elephant's ear? When it's noon on the moon, then what time is it here? If you could count for a year, would you get to infinity or somewhere in that vicinity? When you choose how much postage to use, when you know what's the chance it will snow, when you bet and you end up in debt. Oh, try as you may, you just can't get away from mathematics.
Good morning and welcome to day one of online learning with Mr. Weep. This is our calculus class for the first day. We are moving into a new unit and I'm excited to teach this unit. This is a good unit. This is where we get into why we've been doing the things we've been doing for the last little while in terms of derivatives. We are looking at the applications of derivatives. And as you can see on the board behind me, there are three different applications that we're going to look at over the next little while. They are an application of velocity and acceleration, which we have already seen a little bit of. Secondly, there's optimization problems, which are maximum and minimum problems. And if you think back to grade 11, when we did all of our quadratic equations and we were finding vertexes, it's essentially what we are going to be doing again. And finally, we have related rates, and related rates is probably the most useful application of them, but it's probably also the most difficult to learn. And so we're going to work through all three of those in the next little while. So yeah, we're going to get started with an example right off the bat, because velocity and acceleration, you know how to do this already. If you think back to grade 11 physics, and grade 12 physics, in fact, when we had a displacement time graph, we would find the slope of the line in order to find the velocity. And if we had a velocity time graph, we would find the slope of that line to find the acceleration. And so since derivatives is all about finding slopes of lines, that is essentially what we're doing. When we find the derivative of a displacement time function, we are finding the velocity. When we find the derivative of a velocity time function, we are in fact finding the acceleration. So it's really exactly what we've been doing. So I've got an example and we are going to go through it and then you should be good. All right, here we are with our example on the board behind me. Just grab my whiteboard marker. We have the position of a particle that is moving along a line. So it's moving back and forth along a line. And it's modeled by the equation S, which we also call f of t, function of time. And it's 2t cubed minus 21t squared plus 60t. And they'll always put this little thing here because it's important to remember that t has to be greater than or equal to 0, simply because time can't be 0, or it can't be less than 0. T is measured in seconds, s is measured in meters, and away we go. So questions are going to be things like this. What is the velocity after 3 and 6 seconds? So really all you need to do is v will equal to s primed. And we're going to take the derivative of our s function. And so we'll just use our simple power rule. We're going to go 6t squared minus 42t plus 60. All right, so there's our function. And now we want to be able to find the velocity after 3 seconds. We simply put 3 in for t. And we will get our answer of negative 12 meters per second. Okay, so a negative sign, again, just indicates that it's moving to the left. If we add a positive sign, that would tell us it's moving to the right, or vice versa. Really, it doesn't matter which way you choose as positive or negative, but it's moving backwards in time, or not in time, backwards in displacement. All right, and if we want to do it after 6 seconds, we again just simply change the 3 to a 6. And again, really simply. And here we will get a velocity of 24 meters per second. Okay, so that's not so bad, right? We can do that. A second part to this question, and I'm just going to erase this first part. Again, you can pause and replay this as often as you want. So if I'm going a little too fast, you have that option. So I'm going to erase this question. We're going to leave the information on the board. And a part B to this question might be, when is this particle at rest? Well, when a particle's at rest, that means its velocity is equal to 0. So we're going to take that equation that we just found for velocity and we're going to make it equal to 0. So we had the velocity equaling to 6t squared minus 42t plus 60. And in order to make this equal to 0, we are going to want to factor this. And so again, when factoring, the first thing you want to do is take out any common factors. And so the first thing we can do here is divide everything by 6, and including the 0, which will leave us with simply t squared minus 7t plus 10. And if we factor that, we will get t plus 2 and t minus 2 and t minus 5. And that tells us, of course, that the velocity will equal to 0 when t equals to 2 and 5 seconds. Okay, so what we've got here now is we've got a model of this thing moving. For the first bit of time, it's moving in one direction. It stops at 2 seconds, reverses its direction, goes back for up until 5 seconds, stops, and then again reverses and continues on in a different direction. Or it could continue on the same direction. We don't know that yet. All right. A part C to this question, I'm not going to write it down, but a part C could be, when is this particle moving in a positive or negative direction? And so to do that, we want to again look at this factored function. All right, and we want to know what values of t will make this factored form positive or negative. And to do that, we simply pick times that are in between the intervals 0 to 2 seconds, between 2 and 5 seconds, and then greater than 5 seconds. And so if I pick a number between 0 and 2, like 1, then I will have a negative 2, or a negative number inside this bracket, and a negative number inside this bracket, and a negative times a negative would be positive. So this would tell me that it is moving in a positive direction between 0 and 2 seconds. If I pick a number between 2 and 5, like 3, then I will have a positive number in the first bracket and a negative number in the second bracket. And when I multiply those, I'll get a negative number. So between 2 and 3 seconds, it's moving in the negative direction. And if I go greater than 5, like 6, if I put that in here, I'll have a positive times a positive, giving me a positive direction. And so now, in fact, we do know that from 0 to 2 seconds, it's moving positively to the right, stops. For the next 3 seconds, it moves back, stops, and then continues on in a forward direction after that. All right, so that's the way that goes. Now, the final part of this that you could get is, what is the total distance that this particle has traveled in a certain amount of time? In this case, we're going to say, what is the distance traveled in the first 6 seconds? So we're going to call this part C. What distance did the particle travel in 6 seconds? All right. So to figure this out, we have to remember that the formula that we're given, this formula, is a displacement formula. It's a position formula. It's where it is in time after a certain amount of time. And so what we have, if we want to model this thing, it is moving this way. So it's starting here somewhere, okay? And it is moving in this direction for 2 seconds, all right? And then it stops here, okay? And then it's going to come back for 3 seconds, okay, to a distance somewhere, we don't know where, but maybe we'll put it here, and then it's going to turn around again and go in this direction up until 6 seconds. Okay, so it's going this way, then it's going back this way, and then it's going back to the right. And this is of course what our particle is doing. Now, if we were to just put 6 seconds into here, all that's going to tell us is the displacement from the beginning to the end. So we don't want to just put 6 in. What we have to do is we have to split this up into pieces. We have to go from the time of 0 here to the time of 2 here. All right, how far has it traveled in that section? And for that, we can simply do f of 2, right? Function with t is 2, put that in, and we will get the distance, because at this point, the distance and the displacement are the same. So if we do that, it goes like this, we're gonna go s of 2 equals that's supposed to be a 2 squared plus 60 times 2. And if we do that, we will get a distance or a displacement of 52 meters. All right, now, after this, now we have to find how far it travels in these next 3 seconds. And to do that, we have to set up a little thing. We have to say, okay, well, what is its position after 3 seconds? And we're going to use absolute values because we need a positive number because distances can't be negative. Displacements can be negative. That tells you what direction the displacement is in, but distances cannot. So we're going to go s of 5, because that was at 5 seconds where it stopped here, minus s of 2. So its position here minus its position here will give us the distance that it traveled in those. All right, so now what you're going to do is you're going to put in 5 for t, you're going to put in 2 for t, and you'll calculate your answer. And in that case, you should get a 27 meters. Okay, I'll let you do that calculation on your own, but again, you're going to put in 5 for t, then you'll put in 2 for t. You'll probably get a negative 27, but again, it's the absolute value, so in the end, it is a positive 27. And then you're going to do the same thing from where it is after 6 seconds, s of 6 minus s of 5, and again, absolute value. So again, you're going to put in 6 for t, you're going to put in 5 for t, subtract those two numbers, and you will get 11 meters. And then, of course, to find the total distance, you will simply add those three numbers together to get a final answer of 90 meters. So that's the way velocity and acceleration questions work. Simply finding the derivative. And again, we weren't asked about the acceleration in this question, but we certainly could have been. And if we were asked for the acceleration, we would be finding the second derivative of our position function. The first derivative was velocity. The second derivative would give us the acceleration. And then we could find questions related to acceleration on that. So in your assignment, you will get some questions that involve objects that are moving up and down. And of course, then we know the acceleration, but there could be an acceleration formula in terms of finding time, etc., using the acceleration formula. So that's it for today. Your assignment will be partially out of your textbook, partially out of the other textbook that I've been using, and you can find that on the Connect page under assignments. So there will be a video link to this, well, you've already watched the video, so you know there's a link, and the assignment will be found on Connect as well. And again, if you have any questions, feel free to reach out to me by email or by phone, and I'll be happy to answer any of your questions. Have a great day, and we'll see you in a couple of days.